In question 2 of this series, we're asked, a hemispherical tank is filled with water having a density of 1,000 kilograms per meters cubed. Find the work needed to pump all of the water to a height of 3.25 meters above the top of the tank. So what we have here is an illustration of what's going on. We have a tank and it has a radius of 2. Take a look. And what we have to do is pump all of this water to a level of 3.25 meters. Before we start doing the math, take a look at the formula for work. Work is defined as the amount of force times the distance. What we have to do is come up with a formula that we can represent as force times the distance and then integrate that to find the amount of work using this relationship. Now, because we're moving up, we will have the formula in terms of y. I'll start by writing out work is equal to force times the distance. We'll need to define what force is and distance is. I know that force is equal to the weight of the water times the constant 9.8 newtons per kilogram, which is useful for measuring the force applied by gravity on each kilogram of mass. Now, I don't know the weight of this water, so I need to define weight now. Weight is equal to the volume of the water times its density, which is given to us. Now, to find the volume of this hemispherical tank, we have to refer back to one of our lessons where we learned how to find the volume of solids. One of the techniques we used was to find the volume of tiny cylinders running along the y-axis, and whose radius was the function representing the shape. A link to that lesson is provided in the description below. And so to find the volume of the solid, we will use the formula pi times the integral between 0 and 2, r squared, which represents the function dy. And if the cylinders are running along the y-axis, which they are in this case, you have to make the function in terms of y. So you have to solve for x. Now, of course, this function can be written as dv over dy is equal to pi r squared. This number will now be multiplied to the density, which is 1,000, that was given in the question, and we'll take this expression and place it right here, because by multiplying these two, we found the weight and we can substitute that into there, where we get force is equal to pi r squared times 1,000 times 9.8. I know I mentioned this earlier, but this r represents the function itself that's making this hemisphere. And the function that makes this hemisphere is r squared is equal to x squared plus y squared, where r is the radius. It's a constant number technically. So we'll be replacing this with the version of this formula where we have x is equal to, and we want the formula to be in terms of y as opposed to in terms of x. So let's go ahead and do that right now. We will solve for x by bringing this y over. R squared minus y squared is equal to x squared, and we can square root both sides, where we get x is equal to 2 to the power of 2, because our radius is 2. So 4 minus y to the power of 2 square rooted. I'll be replacing this r with the following function, and subsequently I'll take this function and place it into here, where I have work is equal to pi times this thing to the power of 2, leaving us with 4 minus y squared times 9,800. And lastly, we need to find an expression that represents distance. Now, as you take the volume of these cylinders all throughout the shape, d represents the distance of that cylinder to the top. So we can say that since we don't know where that cylinder will be, while we take the integral to find the volume of this hemisphere, the variable distance can be represented as 3.25 plus y. So I'll put down 3.25 plus y. And this is all with respect to dy. So, by integrating this function, I'll find out the amount of work needed for this process to occur. So I'll take the integral between 0 and 2. I'll pull out all my constants, outside, leaving me with work is equal to 9,800 times pi times the integral between 0 and 2, 4 minus y squared times 3.25 plus y. The next step is to expand the expression. And by expand, I mean take this number and multiply it to the two numbers in the adjacent bracket, and the same thing with this term. And from here, I'll use my calculator to integrate by clicking this and substituting my function into here. 4 minus, and I won't use y, I'll use x because that's the way our calculator is configured, to the power of 2, 3.25 plus another x. And now we put our bounds between 0 and 2. That gives us 64 over 3. We'll multiply this number now by 9,800 times pi. And this gives us approximately 657,000. Because we have three significant digits that we're working with, 3.25. And everything after this 6 is insignificant. So we have 657,000 newtons times meters is equal to the amount of work. And so there you have it. That is how to find the amount of work needed using integrals.